Hello friends, I'm going to discuss about certain points which are absolutely necessary for understanding Fourier series, Fourier transform and Laplace transform. So the topics that I'm going to cover in this chapter in this video is difference between Fourier series and Fourier transform, discrete or continuous spectrum for Fourier series and Fourier transform, relation between Fourier transform and Laplace transform, region of convergence properties and reason behind it. So now let me just start by making a statement. The statement is most of the signals that we come across in nature are all made up of sinusoidal signals. This point is very important. You have to understand it very clearly. Most of the signals that we come across in nature are all made up of sinusoidal signals. And one thing that I'm going to tell you is that these signals, Dirichlet conditions must be satisfied, and fortunately most of the signals that we come across in nature, they satisfy Dirichlet conditions. You can find these Dirichlet conditions in any standard book. So now let us go through the basic logic behind Fourier series. Fourier series is applicable for periodic signals which do not have any infinite magnitude at any particular point of time, at any instant of time. They should not have infinite value. You can think of any periodic signal like this. This is a periodic signal, or you can take this periodic signal or any periodic signal as you want. But its magnitude should not be infinite at any point of time. So now when you take such an signal and perform its Fourier series analysis, you get an output, an infinite sum. I have just written sum here. It is actually an infinite sum of sinusoidal signals of different frequencies. And the interesting property about these frequencies is that these frequencies are integral multiples of original input function frequency. For example, the frequency of this signal is omega naught. Then these signals will have frequencies as omega naught, 2 omega naught, 3 omega naught, and so on till infinity. So we can have infinite terms here, we will have infinite terms here, and the frequencies will be like omega naught, 2 omega naught, 3 omega naught, as such. So when we want to plot the magnitude spectrum of these sinusoidal frequencies, for example, we take one frequency, one sinusoidal function, one sinusoidal signal of one frequency, it will have one magnitude, all right. And when we want to plot it on a graph, then we will have the values of values of magnitude only for one frequency. For example, for we will have omega naught frequency, we will have 2 omega naught frequency, we will have 3 omega naught frequency. But what about the frequencies which are not which are between these frequencies? For example, 1.5 omega naught, zero point 0.5 omega naught, and all other frequencies. We do not have sinusoidal functions of those frequencies. So we can say that Fourier series spectrum is actually discrete spectrum, because we have different discrete frequencies, only discrete frequencies in the spectrum of this Fourier series. Now let us talk about Fourier transform. Fourier transform is actually applicable to non-periodic signals, and again, the whatever signal you think of, it should not have infinite magnitude at any point of time. And for example, I take this signal, and when I do Fourier transform analysis of this signal, what I again get sinusoidal signals, but now this time the frequencies are not discrete, they are not integer multiples, they can be any value. Frequency can be of any value from minus infinity to plus infinity. All these points contribute in the spectrum, all these frequencies contribute in the spectrum. What does it mean? That we will have so many sinusoidal functions of different frequencies, all frequencies. So we can see here that this graph is continuous. So that is why we say that Fourier transform is actually having continuous spectrum. So now the basic idea behind Fourier series or Fourier transform is that, for take an example, when you put white light, when you throw white light on a prism at the input, what you get in the output? We get colorful lights. We get different components of colors in the output. Similarly here, when you take any signal, periodic or aperiodic, and do its Fourier analysis, for periodic signal you do Fourier series analysis, and for aperiodic you do Fourier transform analysis, then in the output you will get different sinusoidal functions. These sinusoidal functions, when you add them together, then you what do you get? You get the original function, original signal. So this discovery which was made, when it was made, it was such a nice breakthrough in the signal processing technology. So now let us know about relation between Fourier transform and Laplace transform. So this is the relation for Fourier transform. X omega is equal to integration minus infinity to x t e raised to the power minus j omega t dt. And for Laplace transform it is xt into e raised to the power minus st dt. Here s is equal to sigma plus j omega. All right. So when I put value of s here, I get xt into e raised to the power minus sigma t into e raised to the power minus j omega t dt. This is simple mathematics. So now when I put them together, xt into e raised to the power minus sigma t, we name it x dash t. So if we look at this equation, and if we look at this equation, what can we infer from these equations? We can say that Laplace transform of xt, this is Laplace transform of xt, is equal to Fourier transform of xt into e raised to the power minus sigma t. This is xt into e raised to the power minus sigma t, and when I multiply it with e raised to the power minus j omega t and take its integral from minus infinity to plus infinity, it becomes the equation for Fourier transform. All right. So instead of xt here, we get x dash t. Instead of Fourier transform of xt, we get Fourier transform of x dash t here. So this is Laplace transform of xt, and this is Fourier transform of x dash t. They both are equal. Hence we can say this Laplace of xt is equal to Fourier of xt into e raised to the power minus sigma t. Now we have to focus on this term, e raised to the power minus sigma t. This is very important. Now, as I have told you already, that Fourier transform does not exist for functions that are not finitely integrable. What does it mean? That from time minus infinity to plus infinity, the value of the function, the magnitude of the function should never be infinity. But if the function's magnitude is infinity at any instant of time, then it is not finitely integrable, it is not absolutely integrable. For example, take this function e raised to the power at ut. If I draw its graph like this, then as you can see that as t tends to infinity, the magnitude of this function, it also tends to infinity. Hence, this function is not absolutely integrable. Hence, I have shown it here mathematically. The function is not absolutely integrable. Its integration is tending towards infinity, and that is why Fourier transform does not exist for this function. But as we'll see, its Laplace transform does exist. Now we will see how its Laplace exists and Fourier doesn't exist. Xt is equal to e raised to power at ut, and Laplace transform of xt will be written as this: e raised to power at e raised to power minus st dt. S is equal to sigma plus j omega. We write s in terms of sigma and j omega, we will get this. Then by combining these two terms, we'll get e raised to power a minus sigma t into a e raised to power minus j omega t dt. Now see here, this function, which function, this function in the circle, this function has to be absolutely integrable, so that this whole integration converges. So now our goal is that this integration, this e raised to the power minus e raised to power a minus sigma t, this function, we want this to be absolutely integrable And for making this absolutely integrable, we can see that this function has to be in decreasing manner with respect to time. You can see that time limit is 0 to infinity. So if you plot this on time axis, then I want this to be in decreasing manner. If it is in increasing manner, then for t tends to infinity, the magnitude of the function will also become infinity, and this integral, this won't be converging. It won't exist. This transform won't exist. So what I want this exponential to be decreasing for positive time t. All right. So for making this decreasing function, what I want sigma to be greater than a. If sigma, suppose a is 2 and sigma is 3, then 2 minus 3 is minus 1. So it becomes e raised to the power minus t, and e raised to the power minus t, it is actually absolutely integrable. So that's what I have written here. For sigma greater than a, this function, it becomes absolutely integrable, and hence in that scenario, the Laplace transform of e raised to the power at, it exists. So what I am going to tell here is that when I'm trying to find Fourier transform of e raised to the power at, the transform does not exist. But when I talk about Laplace transform, there is an extra term e raised to the power, there is an extra term, this term e raised to the power minus sigma t, and when we multiply that term with this function xt, then we want the multiplication to be uh, we want the multiplied function, the net function, to be such that it is absolutely integrable. That's the whole point of introducing Laplace transform. All right, I hope now you are clear about this. So now I want to talk about region of convergence of Laplace transform. So what do you understand by region of convergence? Region of convergence is actually an area, a region, which is defined by those values of sigma for which function xt into e raised to the power minus sigma t becomes absolutely integrable. For example, this this is S plane. This x axis is sigma, y is j omega axis. So for sigma equal to 2, I have drawn this region of convergence in the right hand side of this sigma. That I mean that region of convergence is existing for sigma equal to 2. So take an example like e raised to the power 2t ut. Its region of convergence will be like this, and when we take this function and multiply this e raised to the power minus sigma t term, we'll get overall function, this function. And for this function to be integrable, what I need this sigma to be greater than 2, right? If sigma is smaller than 2, then this function will, for example, take an example, take sigma 1 and this is 2. So 2t minus t will become t. So this whole function will become e raised to the power t. And since our limit is from 0 to t, time limit is 0 to t, because this is ut function's time limit is from t equal to 0 to t equal to infinity. If you integrate e raised to the power t from 0 to t, then it won't be integrable, it becomes infinity. So we don't want that. We want that this whole function remains decreasing sort of function. So for that, sigma has to be greater than 2. Here sigma, for all these values are greater than 2. These values of sigma are greater than 2. So we can say that region of convergence, this can be the region of convergence, and this for values less than 2, this cannot be the region of convergence for Laplace transform. So now see here, this e raised to power 2t ut, this is right sided signal. All right. So I am saying that region of convergence is towards right side of sigma equal to 2, that is for sigma greater than 2. I have just told you that region of convergence for a right sided signal, should be towards the right side of this sigma value. You will, for any function, you will find a sigma value just at the uh, boundary of this region of convergence, and you have to then decide that region of convergence is towards the right side of the boundary or towards the left side of the boundary. So for right sided signal, this region of convergence is towards the right side of the boundary. I have told you the logic here. So now we will see about left sided signals. Take an example, e raised to the power minus 2t u minus t. We write it in Laplace transform equation. This is the Laplace transform equation. Because of this u minus t, the limit becomes minus infinity to 0. This is a left-sided signal. All right. Now, when you write s in terms of sigma and j, it becomes like this: e raised to the power minus 2 minus sigma bracket t and e raised to the power minus j omega t dt. All right. So we focus on this function e raised to the power minus 2t minus sigma t. If sigma is less than minus 2, for example, sigma is minus 3, so minus 2t minus of minus 3 becomes plus 3, and plus 3 minus 2t, it becomes t. So it becomes, overall function becomes e raised to the power t. But since the limit of the time is negative, sense it is in negative side, so if we draw e raised to the power t function where time is in negative, so as t tends to infinity, the function becomes e raised to the power minus infinity, and the value would become 0. So we can say that the function, this overall function, it is absolutely integrable in this time limit from 0 to minus infinity. So we can say that the transform of this function is, it does exist. All right. And if we talk about region of convergence of this function, we can say, we have seen here that this function will converge, its integral will converge if sigma is less than minus 2. So we can say that this is the boundary of the region of convergence. Boundary value of sigma is minus 2, and towards the left side, if we make sigma smaller and smaller, it will be a part of the region of convergence. And if we make sigma greater than minus 2, then it won't be a part of region of convergence. So here we can say that for a left-sided signal, the region of convergence is towards the left side of the this S plane. All right. Now we want to see, I want to see what happens during finite duration signal. This is a finite duration signal. I have just taken an example. You can take any signal which is of finite duration. What does it mean by finite duration? Finite duration means it exists only for a finite interval of time, and beyond that interval, the magnitude of the function is 0. And one condition I give you here, that you have to keep in mind that the function should not be infinite. Value of the function should not be infinite in this time interval. So now you have to multiply this function xt. Suppose you want to find its Laplace transform, and then what do? You multiply this function xt with e raised to the power sigma t. All right. And if sigma value is positive, if value is positive, the function will become ever increasing. As you increase t in positive direction, the function is exponential is increasing. If sigma is negative, then it will be like this. So what you have to see here, that since this function is existing only a time limit, only a time band, so whatever time band you select, the function of the exponential, this exponential or this exponential, both these exponentials values in that particular time limit, any time limit you can, any function having any time limit you can select. So whatever time limit you choose, the values of these exponentials will be finite only. So if you multiply this function with this function or this function, in both these cases, the overall function will be absolutely integrable. It won't depend on the value of sigma. you can choose any value of sigma here. So I've written here, take any value of sigma, you either get increasing exponential or decreasing exponential. So you can say that region of convergence is whole S plane here. It won't depend on the value of sigma. Whatever value of sigma you take, the integral, the Laplace integral will converge, and hence the region of convergence is whole S plane in finite duration signals. Now, let us talk about two-sided signals. What happens with two-sided signals? This function e raised to the power minus 3t ut is a two-sided signal, and this e raised to the power 4t u minus t is this function is right-sided signal, and this function is left-sided signal. As I have told you previously, that for right-sided signal, the value of sigma should be greater than the value for boundary value of sigma. So boundary value of sigma is minus 3 here. So for convergence, the region of convergence, sigma should be towards right side for right-sided signal. So for being in right side, sigma should be greater than minus 3 here for this function. And for this function, this is left-sided signal, so sigma should be less than 4. This 4 is the boundary value of sigma. So this sigma should be less than 4, so that it region of convergence is towards the left side of the S plane. So we can see here, I have explained this in detail. 3, we multiply this function with e raised to the power minus sigma t, it becomes minus 3 minus sigma, and sigma, when sigma is greater than minus 3, for example, sigma is minus 2. So minus 3 minus of minus 2, what it becomes? It becomes minus 3 minus t e raised to power minus t, and as you make t tends to infinity, it becomes e raised to power minus infinity, and its value is 0. So this becomes integrable, and similarly I have shown here that this function is also integrable. All right. So if I want to draw the region of convergence for this signal, it is towards the right of minus 3. This is the function, and towards the right of the function region of convergence is this. And for this function, this is the boundary value of sigma 4, and it is towards the left of this value. So since the net function is the sum of these two functions, the region of convergence of the net function, it should be common to both these regions. So if you see here, the region of convergence is the common region of convergence is this. So this will be the region of convergence for the total function, for net function. This will be the region of convergence. If suppose this region of convergence was towards left of this minus 3 value, and this region of convergence was towards right of value 4, then in that case there would have been no common ROC, and in that case we would say that Laplace transform of the function won't exist. So at the last, I want to tell you one more point, that how can we judge just by looking at the region of convergence of a function that Fourier transform exists or not. So if region of convergence has j omega axis, then its Fourier transform exists for xt. If suppose this is the region of convergence of a Laplace transform for any function xt, and this is the boundary value of sigma, and if convergence region is towards the right, then this is the j omega axis, it is not a part of the ROC. Hence Fourier transform won't exist for this function. And similarly in this case, ROC has j omega axis in it, so Fourier transform exists for this function. And similarly in this case also, the ROC has j omega axis, and hence its Fourier transform will also exist. So now that was all I wanted to tell you about these series and transforms. So please share and subscribe and like this video if you want to see more videos in the future, and I will try my best to explain things from a simple and easy point of view. Thank you.